Welcome guys. Today we are going to study about the transform circuits and the S-domain circuit analysis. First of all, I would like to remind you guys that we use the S-domain, or we convert the voltages and current waveforms into its transforms, and the circuit itself to the S-domain circuit or the transformed circuits. And the differential equations that we get for the circuits, we transform them into the algebraic equations, and then we solve the algebraic equations, which are in the forms of sums and differences, and much easier to handle compared to the differential or integral equations. And once we solve them, we can convert them back into the time domain, and we get actually the answers. Though this is wonderful and unique thing or benefit from the transformations that we do using the S-domain. Beside this, there is another wonderful thing of the S-domain, that is the transformation into the transformed circuits. So if we do that, actually it makes many things easier, even further. And now we would like to see some of the element constraints in the S-domain. And in the time domain, if we have a voltage source which is represented as V of t, if this is the source in the circuit, then the current will be dependent on the circuit actually. And if we take its Laplace transform in the S-domain, we can represent these sources just as V of S as Vs of S is the source, and the current will be dependent on the circuit. So you can see that there is quite much similarity in the time domain and in the S-domain. And similarly, if you see for the current source, if there is the current source which is the independent source, in that case the voltage of the circuit will depend upon this current. So if we transform it into the S-domain, you can see that this time is replaced with the S in the S-domain. And similarly in the S-domain, the voltage source will be dependent on the circuit. The voltage will be dependent on the circuit if current is the independent source. And if we would like to show these things with the help of the circuits. You can see in this circuit, apparently we can see this is the voltage source in the circuit. So the current will be dependent on this, and this voltage is actually the voltage which is supplied by this source to the external circuit, whatever is connected on this side. And similarly, this is in the time domain, and after the Laplace transformation, those can be represented in the S-domain, just replacing that. And similar, it is the same for the current source and shown in the S-domain. And after having done this, we will actually now see some more theoretical concepts. Further, because of the linearity property of the Laplace transformation, the voltage controlled voltage source in the time domain, after taking the Laplace transform in the S-domain, it will turn as voltage controlled voltage source dependent on the S rather than time dependent. Similarly, the current controlled current source will be transformed to this form, and the current controlled voltage source will be transformed to V2 of S into R into I1 of S, where we can clearly see that this current and this current only have the difference of this is time dependent and this is S dependent in the S domain. And depending on this current, this is the voltage source. Depending on this current, this is the voltage source. So this is also changed from time to S domains as just like the other sources. And the last one, the voltage controlled current source can also be represented as voltage current source dependent on the factor G, or dependent on this voltage in the S domain. And next we can talk about some more concepts.
Okay.
Now S-domain models for passive elements using voltage sources for initial conditions and models for passive elements using current sources for the initial conditions. We know the passive elements in the circuits or in the electrical engineering are the resistors, inductor and the capacitor. For resistor, we have the mathematical model as V is equal to R into I. So if we present it into the circuit form, we can present it like this. Just using the linearity property of the Laplace transform, we can write this into the Laplace transform as this one, and the circuit will stay the same, and the variables will be represented in the S domain. Now we come to the inductor. For the inductor, we have the differential equation V is equal to L into DIL over dt. And if we form the circuit of for the inductor, that is this one. Since this is written in the model for the inductor is represented by the differential equation or by a formula which has the differential in it. So we will have to use the differential property of the Laplace transform to convert this into the S domain. And we know this in the S domain, this is actually the conversion for this differential equation from here, but it contains the initial condition. So if we form the circuit using this one, we will find out VL of S is equal to Ls into ILs of S minus L into IL of 0. So this is actually our circuit in the S domain. But in this one, we can clearly see that this is a current controlled voltage source, and this source is dependent on the initial condition of the current in the circuit. We can also similarly find for the capacitor. For the capacitor, since we know that IC of t is equal to C into dVc of t over dt. So from this one we find out the Vc. So this will turn into an integral equation, and in the time domain we can simply present it with the capacitor, with the source. So since this is in the form of an integration, so we will have to use the integral property of the Laplace transform, and using that one, what we are going to get is this one. And you can also see this in the Laplace transformation table as well. So for this one we have found this one. So now we have to use this one to find the circuit of it, which is Vc of S is equal to 1 over Cs into Ic of S plus Vc of 0 over S. So this is a voltage controlled voltage source here, and this circuit is actually replaced by this circuit in the S domain. So wherever if you have to just convert the circuit from the time domain to the S domain, you can, if you find the inductor, you can simply replace that portion of the inductor with this circuit. So this one is equivalent to this one, and this one is equivalent to this one from time domain to the S domain. So these are the models for the passive elements using the voltage source for the initial condition. So we have used the voltage source as the initial condition. Now we can also change it in such a way that we use the current sources in places of the voltage sources for the initial conditions. There are two ways to see it. One is this way, that you can simply use the source transformation from here. For example, this is the reactance, Ls is the reactance. So using this one, and this is the voltage actually. So if you divide this with the voltage, this one, you will actually get the current. So that current will be simply, you can clearly see that this voltage is L into I L of 0 divided by Ls. L is cancelled out with the L. So what you are getting is I L of 0 over S, which is already written here. So since this is with a plus sign, so this will be leaving this node. So you can clearly see, and Ls, this reactance just like resistance will come into the parallel of it. So you see, using this source transformation, you can find, you can also show this same circuit in the S domain with this circuit as well. So this is all dependent on your choice, and actually dependent on the circuits that you will have. Whatever you feel easy, you can use one of these both. Both are equivalent to each other. And if you write it in the form of the equation, you can also find, just like as you have written an equation for you have an equation here, VL of S is equal to Ls into IL of S minus L into, this is KVL, and if you use the KCL, you can write here IL of S is equal to the current that which is going to this direction, and then the current which is going here. So the sum of these two currents is equal to this one. So it means IL of S is equal to VL of S divided by L of S, since this voltage is equal across this one and this one. So VL of S divided by Ls, and plus this current, you already directly have it, IL of 0 over S. So you see, you have found this equation and this equation, actually those are equivalent. Just in this one we have it in the form of VLS as output, and in this one we have IL of S as output. So these are the representations in the S domain for the cases, for the case of inductor. Similarly, for the capacitor case, we have already talked about this one, and if you use the source transformation here as well, you can see this is the voltage and this is the current, this is the impedance. So if you divide this voltage divided by this impedance, you will actually get this here, and this impedance will stay the same in the parallel. And if you write the equation for this one, IC of S is equal to this impedance, this voltage divided by this impedance. So you are going to get this one, and you can actually also write it like CS into VC of S minus C into VC of 0. So this is actually the representation in the S domain. So this circuit and this circuit both are equivalent to each other, and this equation and this equation both are equivalent to each other, just the difference. So both of these equations are equivalent to each other. So this is how you can show, as per your choice or as per the situation in the circuit you are dealing to solve, or you are solving them, or you are doing the analysis, you can either use this one or this one as per your circuit demands. So this was the model's representation from the time domain to the S domain. And in the time domain, you could see that these were represented just as normally you know that this is simply a resistor, inductor and capacitor. But in the S domain, these will not stay as simple as you see here. Those will be replaced by having the components which are also dependent on the zero condition, because you know that when the when you are dealing with these passive elements, inductor or capacitor, they store some energy if they have been connected to some source, voltage source or the current source. So accordingly they save some energy, and those energies are part of the circuit to be shown if you want to do the proper analysis. Now we are going to solve this circuit, and this circuit is given. This is our voltage source for this circuit, and the initial condition is given IL of 0 is equal to IA. So for this given circuit, what we have been asked to find out: transform the circuit into the S domain, then solve the current transform for I of S, and then find the waveform for I of t by taking the inverse Laplace transformation. So first of all, we have to convert this circuit into the S domain. So let's do the solution. Solution for A part is the voltage source will remain the same as we have already talked about it today. However, here we see Vs of S will be equal to Va into e to the raised power minus alpha of t. If we take the Laplace of this function, Va into e to the raised power minus alpha t, Va is constant, and e to the raised power minus alpha into u of t, where this is the u of t is the unit function. So for this function, exponential function, the Laplace transformation is s plus alpha. So this is our transformation to the S domain for this function or this waveform, source waveform. And after that, the resistor, we have just already noticed that R remains the same. And this inductor, on the other hand, will turn into Ls in the S domain, minus plus this will be L into IL of 0. Since for the inductor we know the equation VL of t is equal to L into DIL of dt, taking the Laplace of this is equal to VL of S is equal to Ls into I of S. Now in this circuit, Ls into I of S minus L into ILF 0. So this is current controlled voltage source, and we have already talked about this. So this is actually now our A part solution. This is the transformed circuit or the circuit in the S domain for this time domain circuit. The B part, we have to solve the current transform. So we need the current I of S. Using KVL, we can write the equation for this. So let's first write in the most general form, Vs of S, this source Vs of S, plus R into I of S plus L S into I of S, since this is the reactance just like the resistance but for the reactive load, minus L into IL of 0 is equal to 0. So we can simply count once again 1, 2, 3, 4. So sum of 4 components will be equal to 0, 1, 2, 3, 4. So Kirchhoff's voltages law has given us the equation, and now we have to solve this equation. To solve this equation, for what? For I of s. So this is common here, and we can take the rest of the expression to the other side, which will Vs of s plus L into IL of 0. Since this is negative, going to the other side both becomes positive, and I of s is equal to Vs of s plus L into IL of 0 divided by R plus L into S. And in this one we can actually further simplify it. We can also substitute the value for V of S, which is this one, VA over S plus alpha, VA over S plus alpha plus L into IL of 0 divided by we can take out L common from this one, so this will become S plus R over L. We have just taken L common so that to keep S independent from any term in its coefficient. So I of S is equal to, we can now separately write VA over L divided by S plus alpha into S plus R over L plus L into IL of 0 divided by L into S plus R over L. So now we have to simplify it further, or actually we got our I of S, which is VA over L divided by S plus alpha into S plus R over L plus this L and L is cancelled out, so IL of 0 divided by S plus R over L, and actually we have been given the value for IL of 0, which is IA, so we can simply replace this value here as well, which is IA. So this is our solution for the second part. Now we have to find out our last solution, or solution for the last part, which is perform the inverse transformation to find the waveform I of t. So we have to take the inverse Laplace transform of this one, which will be the solution for the last part, and we can solve it here. We can also erase this one to get some more space, and this will also be so in this one we can first see that this is already in the simplest form, but this one we have to solve it. We have to do the partial fraction 1 over S plus alpha into S plus R over L is equal to, these are linear, multiplied, or multiple linear functions being multiplied. So a over s plus alpha plus b over s plus r over l, which 1 is equal to a into s plus r over l plus b into s plus alpha. So for s is equal to minus r over l, we will get 1 is equal to b into minus r over l plus alpha. So b is equal to 1 over alpha minus r over l. Similarly for s is equal to minus alpha, we will get minus alpha 0. So 1 is equal to a into minus alpha plus r over l, and this is a is equal to 1 over alpha minus r over l. Since I have taken minus common from here, so minus will come to this place. So this is our a. Now we can simply replace them. I of s is equal to VA over L, VA over L, and for the rest of this we can write A, that A is replaced with minus 1 over alpha minus r over L divided by s plus alpha, and plus B is equal to 1 over alpha minus r over L divided by s plus r over L, and the second part is IA divided by s plus r over L. So now we can actually take the inverse Laplace transformation, taking inverse Laplace transformation. I of t is equal to VA over L minus 1 over alpha minus r over L. This is e to the raised power minus alpha t plus 1 over alpha minus r over L into e to the raised power minus r over L into t plus IA into e to the raised power minus r over L into t, and this will whole be multiplied with the unit function in the time domain. So this is our solution for the last part. So this is our waveform I of t, the required. We can also rearrange it in such a way that we can combine these terms together in the forced and unforced functions. So I can write that one here as well. I of t is equal to minus VA over L into alpha minus R over L, minus VA over L into alpha minus R over L into e to the raised power minus alpha t. And further, plus VA over L into alpha minus R over L plus IA into e to the raised power minus R over L into t. So this is VA over L into alpha minus R over L, and then plus IA, and this one is the same coming outside of this one, and we can whole multiply it with the u of t. So this is our, we can also write it this form. So we have noticed that we solve, first we transform the circuit into the S domain, then we solve for the current transform, and then that was converted back into the by taking the inverse Laplace transformation into the I of t. So this is how we can actually solve or do the analysis for our given circuit. And we can simply now here we can see by changing time we can see the response of this circuit easily. So given the values of R, L, and for the initial condition, we can simply see how this circuit is behaving. And that's all for today, and I hope you will enjoy it. Please try it, and if you find any difficulty, please comment in comment and ask for a solution if you want to find solution for any other question as well. Thanks. Bye.